Hello, everyone. So this talk is demystifying the physical layer, how the magic is done. I hope it doesn't create too much hype. But we will start with our past. So who has used srsRT? 1, 2, 3, 4, 5. OK, who has done more than 75 megabits with srsRT? No one did more than 75 megabits? OK, we are not doing good then. OK, so let's go back. What we supported in our SRS InnoDV. So we supported up to 20 megahertz bandwidth. With 2 antennas, we were able to reach 200 megabits per second in every sector. And we could scale our processing to 4 cores. In our benchmarks, with an overclock CPU, we could reach 400 megabits per thread in the downlink and 100 in the uplink. I don't know how you feel about this, but to me, it looks very low. So then what are we doing now with our GNODV? Well, our GNODV is going for 5G. So we support 100 megahertz for antennas and 4 layers. And we target a downlink rate of 1.4 gigabits in the downlink, which is much higher than 4G. So now we just went from 4 to 100 cores. Like we can scale our GNODV to many more CPU cores. And then we could even achieve by 1 thread with an overclock CPU to 2.5 gigabits per second, just doing PDSCH. And in the uplink, 300. So yeah, that's pretty high. So now what I will talk about, I will concentrate in the upper physical layer, just like channel coding, estimation, and so on. And I will present which are the tools and strategies we use to achieve this 1.4 gigabit per second, like how to achieve these rates, and how to scale, what we did for scaling our processing. Then I will focus only on data channels, so I will not mention PUCCH or PDCCH at all. And I will do a very high level of description. So I will not say anything about low level, like how the LDPC decoder works, because I think this is too complex. And in today afternoon, it wouldn't be enough time for this. I will not mention any 3GPP at all. So not TS 3 point whatever, because that's not possible. And I won't show any simulation results, maybe some benchmark, but everything that we're showing runs for real in CPUs, which are available for consumer and maybe some industrial market, but it's all available. OK, so the talk will present some physical layer specifications. Then I will present which are the key strategies and tools to achieve the performance I will describe in the specifications. Then I will give some performance figures and traces to show and prove that this is possible and runs. Conclusions, and then there will be the space for questions. OK, so we start. Well, I guess everyone knows what the physical layer is. It's at the bottom of the SI model. It does modulation, channel coding, estimation, equalization. We all know about this. Then the question now is, what is the upper physical layer in the Open RAN? Well, the physical layer is divided in 2 parts, the upper PHY and the lower PHY. The upper PHY is the one that will generate the signals, like sounding reference signal, reference signals, the signal detection, equalization, decoding. And then the lower PHY will be the part that it will modulate, demodulate, it will synchronize with the it will be in the RU side. OK, then the 3GPP says many physical layer channels. Like there are channels for data, channels for control, reference signals, and synchronization. However, the ones that are really consuming lots of performance are the data channels. And those are the PDSCH and the PUSCH, which is physical downlink shared channel and physical uplink shared channel. OK, so on the downlink side, the PDSCH, the process of the PDSCH could be divided in 2 parts. From a transfer block, we first do encoding. And once encoding is done, we do the modulation. There are many steps, but that's basically the steps. And then whenever we are modulated the PDSCH, we send it to a radio unit over the open front hole. This would be the steps for the PDSCH. And then for the POSCH, it would be the opposite. We will get a resource grid from the radio unit. And then the first step is channel estimation, then the modulation, and then the multiplexing, the control, and the data. Then the data will be decoded and send over FAPI the results to the MAC layer. OK, then let's say the specifications we have. So when we want to optimize our G0V, what we are targeting is TDD with a 30 kilohertz subcarrier spacing. That means half millisecond slots. And more specifically, we normally use 7 slots for downlink, 2 for uplink. Then bandwidth, as I said before, 100 megahertz, 4 transmit and 4 receive ports with 4 layers for the downlink. And we will soon be able to support 2 uplink layers. Then the open front hole with a split 7.2. And with this, we would achieve 1.4 gigabits in the downlink and 200 megabits in the uplink. So to say it with different words, what's the data volume? That would be 1 megabit in half millisecond, which is 2 gigabit peaks of processing for the downlink. And then in the uplink, it would be processing half megabit every 2 milliseconds. So it seems that these numbers are not big at all. But trust me, like processing 1 megabit every half millisecond is really heavy, especially for the physical layer. So now the next question would be, in which platforms are we going to run our physical layer? So in our lab, we have tested a few platforms, but I would like to I'll concentrate in the x86 and ARM. On the x86 family, we use Intel Xeon. For example, in a 24-core Intel Xeon, we can run 4 sectors. And then in AMD EPYC, with 128 cores, we can run 12 sectors. On the ARM side, we have recently done certain improvements. So with a 80-core Ampere Ultra, we are able to run 12 sectors. Then, yeah, so in the beginning of the year, we have some PDSCH benchmarks where we can see what is our processing performance depending on the number of threads. And we had a little issue that when we were reaching around 60 threads, we had this bottleneck on the top. You can see the yellow graph. That's x86. It has a little ceiling around 40 gigabits. So we couldn't get above that line. And then the red line is the ARM architecture, which it couldn't get much higher than 20 gigabits. Well, here are the news. This September, the performance in our EPYC CPU and our ARM CPU are matching. And they reach above 40 gigabits per second. So we made it possible that it's possible to scale the number of threads for processing PDSCH. Then now we go to the next step, is which are the tools and strategies we use to make possible this scalability? Well, first of all, we reduce our memory consumption. There are things that sound very obvious. Like the first step is between the encoder and the modulator to use pack bits. It's like, what? Pack bits? 1 byte, 8 bits, right? That's classic. Well, sometimes certain operations on the physical layer, we don't use pack bits because certain algorithms don't like it. For example, the LDPC encoder, implementing the algorithm with pack bits is a bit complex. So we were using like 1 bit for every byte. So now we move that, so we save 8 times the memory. Well, what else? Our modulator, like when we convert from bits to complex symbols, the natural way to do it is using single precision. Well, single precision means that for the real and imaginary parts of using 4 bytes for each part. But hold on, like the modulation it's a gray encoding. So it wouldn't be enough to use 8 bits for the real, 8 bits for the imaginary, and just a scaling factor. So that's what we did. So we went from 8 bytes to 2 bytes between the modulator and the MIMO precoder. So we save 4 times the memory in this point. And that's a lot of memory to save as well. And then the next big change is using 16-bit floating point on the resource grid. OK, the 16-bit floating point, maybe it sounds a bit too complicated. But with this, we reduce the resource grid memory to 50%. It means like originally a resource grid which is 4 ports, 275 PRVs maximum with 12 subcarriers each PRV. It means that every resource grid is 1.4 megabyte. We say, oh, 1.4 megabyte, like that's nothing. Well, yeah, well, it's not nothing. But if we compare this amount of data with the size of a CPU cache level, it would mean that in order to set to 0 a resource grid, it would take 46.2 times flushing the cache level 1. So that's a complete overkilling for the memory. So what we did is use the brain float, which is basically taking single precision floating point and removing the 16 LSB bits. So with this, we have a marginal, like we lost a little bit of precision in our resource grid, but also we reduced a lot the memory consumption. That was a good breakthrough, and we gained a lot of performance. The next big improvement was changing our interface of the LDPC encoder. So originally, we were encoding all data. It means that we had a code block that we wanted to encode, and we would produce 3 times the size of the code block and feed that to the LDPC rate matcher. So this was making, like, if we want to transmit 1 megabit, then we would have to produce 3 megabit with this. And also using unpacked data, that would mean like 3 megabyte just for the sake of using 3 megabyte. So what we did is change an interface and change the paradigm we operate. So what we do is the LDPC encoder gives an interface that a rate matcher takes, and we process on the fly certain parts of the LDPC. So for example, the LDPC encoder has a systematic part in the code. It has some fixed parity bits, and then it has the extended region. So the LDPC rate matcher, it requests certain parts of the LDPC, and we calculate those ones on the fly. So with this, we reduce from 6 gigabytes of memory bandwidth to 2 gigabytes. But it doesn't sound much, but when you are running like 100 threads, it makes a big difference. OK, another thing that we did this last year was parallelizing on the PDSCH. So the parallelization on the PDSCH is done at code block level. At the level of when we want to transmit a PDSCH transmission, the first thing we do, instead of starting from segmentation, what we do is fork, creating asynchronous tasks, and each asynchronous task selects a portion of the transport block and processes like from the encoding, scrambling, modulation, MIMO precoding, and even the resource mapping is done all in parallel. You could say like, hey, the scrambling, the pseudo-random sequence is not possible to parallel because it requires the previous state before processing it. Well, we found a way to make it in parallel. So we can do all the code blocks in parallel, and everything gets mapped on the resource grid at the same time. Then on the uplink side, we try to do it similarly, but because it has the channel estimation and the equalization before the part where we separate the control and the data, that makes almost not impossible, but it's really hard to parallelize this part. So we perform the parallelization, the forking, just after the multiplex of data and control. That would be in the ULSCH, the multiplexer. So the decoder is basically the LDPC D-rate matcher, like the part that reverts the rate matching, and that's the LDPC decoding, and also the code block cyclic redundancy check. And once all the code blocks are decoded, then we join and we send the the cyclic redundancy check indication to the MAC layer. Then another piece or strategy we use is AVX500. I don't know what's your experience with AVX500. Like, it sounds very promising because it uses like longer vectors. It means that it can process much more data in a single instruction than his predecessors, like MMX or SSE and AVX2. However, results sometimes are slightly different. Well, before we keep going, like the AVX500 12 family of instructions, it has many families. Like, it's like 16 families, if I'm not wrong, and more than 5,000 intrinsics. So sometimes it's a bit hard to find what you want to do. And then you might find some intrinsic that does something you like, and then you find that your CPU doesn't support it. That's something common. But anyway, these are a performance comparison between 3 different CPUs using AVX2 equalizer and the AVX500. So we have an Intel gaming CPU like this 11700, which it has more or less like, I would say like 30% gain using the AVX500, and also the AMD one, like the 7950X, it would show some improvement. And then the EPIC also has some improvement in the equalizer. However, in the LDPC decoder, the Intel one has much higher gain, and AMD doesn't. That's something common I've found around. And I thought it was worth showing because, like some people think that AVX 512 doesn't have any gain, but actually some CPUs don't show any gain, and other ones do. Especially, like, I don't know, like for example, Intel has some improvement, other ones don't. Then if we compare it with the overall PDSCH processing, like the benchmark for PDSCH, yeah. So we can see that there is some improvement in the Intel, the AMD, the gaming AMD, it doesn't really show much improvement. And then the server, the AMD EPIC, well, it gets even worse. So it's not really a game changer for some architectures, but still we have it. And maybe someone finds that a CPU in a deployment just works better with AVX500. Then it comes to the acceleration with the SEC100. Some of you ask if we support it, and yes, we support that. It's available in our srsRAN Enterprise. And then, yeah, it implements the LDPC encoder and LDPC decoder. We use DPDK baseband interface for accessing it. We can enqueue operations to it for encoding and decoding. And it offloads performance up to 50% for 6 sectors and 30% for 12 sectors. So this is the, so depending on the number of sectors, this would be the total CPU utilization. Like, as I said, like for 6 sectors, we have more or less half of CPU consumption. And for 12 sectors, like 30% reduction. OK, now we go to some performance measurements and traces. Like, before I start with measurements and traces, we would configure the G0B in test mode in order to have some synthetic load for it, because connecting UEs, it can be a bit complex. So this gives us some deterministic runs. So we assign 3 threads for downlink processing. This compresses PDSCH, PDCCH, the SSV, and so on. Then we have 1 thread to process PUCCH and PUSCH, the common part of PUSCH would be. And then another thread for PRAC detection for the random access preamble. And then another thread to asynchronously decode PUSCH. This is because the PUSCH decoding, it can be really heavy, and it takes very long time, and it can be done asynchronously in a different thread. So this is a trace. Well, it's hard to see, but here we have an entire TDD period. So each of the green, you see well? Or? Yeah. OK, so the green arrows are the beginning of each of the slots, and then the green boxes are the code blocks. So each of the horizontal lines is a different thread. So you should be able to see, like, we have 3 downlink threads, and are the ones with the green boxes. And then the pink one is the uplink thread, and then the blue boxes at the bottom will be the PUSCH. So this is basically the same trace, but for 5 users and a single slot. With this, we are proving that we can run. This is what I said before. Like, we can perform this forking of a code block level for different number of users, and then join at the back before sending the resource grid over to the radio. So what we see is this: like, there is a point, which is the downlink TTI request coming from FAPI. At this point, we get all the tasks for the PDCCH. We get PDCCH, SSV, non-zero power CSI, and we put all the signals on the resource grid. And then up to the TX data request. At this point, we take the PDCCH transmission, break it into code blocks, fork it, and then join everything for sending in the resource grid. Then on the uplink side, it was a bit hard to see in the trace. With basically what we do is when we receive the resource grid symbols, we process PUCCH and PUSCH, and then we asynchronously create all the processing for the code blocks. And as they finish, we can notify the UCI or the CRC results to the MAC layer. OK, here we'll jump into conclusions. Like, the physical layer, what we observe is like is the most resource-hungry component of our GNOD. Like, it consumes a lot of resources, but still, with our latest tools and techniques, we have been able to process real-time, like the PDSCH and the PUSCH, to have the TDD pattern we said before, and achieving 1.4 gigabits in the downlink and more than 200 megabits in the uplink. 1.4 downlink, yeah, 200 in the uplink. Yeah, and it takes between 4 to 5 cores per sector to process our physical layer, and we can scale with the number of threads. Also, our performance in x86 and ARM is pretty decent, and we can have real time with both architectures. And then we have all the gain of resource flexibility with this architecture. And that's it. Thank you for listening, and yeah, I'm open to questions now.